So, welcome to the afternoon session. So, our first speaker for this session is Massimo Pippi from CNRS Paris, and he will talk about the Bloch conductor formula.
So, thank you very much for giving me the opportunity to speak. Pleasure to thank Charanya and Bhamidi. So, today I'm going to talk about a formula, and everything I'm going to say, it's a joint work with Dario Beraldo. So, this is a formula which enters into a classical theme in algebraic geometry, which is trying to relate algebraic invariants of algebraic variety to topological invariants of the underlying topological manifolds. So, just to make an example, maybe the first example of such a paradigm. So, if you pick a curve, smooth and projective, maybe a plane curve, then the genus of the curve can be computed as some number depending on the degree of the curve. So here we have a topological invariant of the underlying manifold, and it's computed via an algebraic invariant. So there is another example that I would like to discuss a bit, which is the Gauss-Bonnet formula. Or what I call Gauss-Bonnet formula. So the setup is the following. We pick an algebraically closed algebraic field, and let me also fix a prime number different from the characteristic of the field. Then you can choose your favorite proper smooth scheme. And there is a formula which says the following. So I can take the alternating sum of the Hodge homologies and this is, so here I'm taking the Zariski homology, and this is computed as, can be computed as the alternating sum of the dimension of the Hueladic homologies. So sorry, this is over UL. Of the Aladic homologies of my scheme. So again, I have an invariant, a number which is extracted from algebraic invariants of my variety, which is equal to a number extracted by somehow a topological invariant, if you're willing to call Aladic homology a topological invariant. Okay, and of course, yeah. If you are in characteristic, I mean, if you are, say, over C, you can replace this with singular homology. And for the rest of the talk, everything which is about Aladic homology will be called topological. Okay. as you see here, I have only one variety. And so first of all, let me refer to these as GBF. So the Bloch conductor formula is a one parameter version of this formula, of the Gauss-Bonnet one. Okay, so let me say what this means. So I'll have to fix the setups, the initial datum. So first of all, instead of taking a base field, we'll take an Ancyllian tree, or maybe a complete tree. So this just means the spectrum of a complete DVR. And we will also assume that the residue field, so maybe this is spec OK. And the residue field will also be assumed algebraically closed. So what's important here is really that it's perfect, but yeah, for simplicity. And of course, so this is the close point of S, and then there is an open point that I'll denote by eta. So this is the spectrum of K, the discrete field, this discrete valuation field, and I'll also fix a separable closure of these fraction field. Okay, so this somehow replaces the role of K, and then the role of Y is played here by an S scheme. So it has some hypothesis. So let's say P is supposed to be proper. And we also assume that it is generically smooth and maybe flat. And somehow the smoothness assumption on Y here is replaced by the assumption that X is regular. And I'll also maybe, yeah, okay. I'll also fix the relative dimension. So you can assume that this is geometrically connected and the fibers are of dimension D. So you should think of X as a family of variety, of course. So on the generic side, the variety is the pullback along the geometric point above eta. Okay, and this is called the geometric generic fiber. And by assumption, this is a smooth and proper variety. And then you have the fiber over the closed point, and this is called the spatial fiber. And on the other hand, the spatial fiber might well be singular. And in fact, as we will see, the Bloch conductor formula is interesting exactly when this is the case. Okay. Very well. Then I can introduce the formula. Where I do that? Here. So there is this conjecture due to Bloch So, which says the following. So I'll write down some symbols and then I'll explain what I mean. So as a replacement for this term, there is a number called the Bloch intersection number. And the conjecture predicted, the formula predicts that this can be computed as, so I consider the Eladi-Keller characteristic, so okay, maybe as a shortcut, is as usual, is denoted as so. So I consider the Eller characteristic of the special fiber minus the Eladic characteristic of the geometric generic fiber. But then there is an extra term, so these two terms somehow are the analog of this guy. But in the one parameter situation, there is an extra term, which is a new phenomenon. So this is called the Swan conductor. And somehow it's an invariant that depends on the fact that the Eladic homology of the geometric generic fiber is it's a representation of the inertia group. I'll explain this. Okay, so just a remark. If we assume that the morphism P itself is proper, somehow the on the right hand side maybe. So smooth base change and proper base change in Eladic homology tell me that the Eladic homology of the geometric generic fiber is isomorphic to the one of the special fibers, so that these two guys are equal, and the action of the inertia group is trivial, meaning that this term is trivial. So somehow in the smooth case, this formula is just 0 equals 0. And the formula is interesting when the special fiber is singular. So let me introduce these numbers. So the Bloch intersection number was originally defined using localized Chern classes. So it's a quite complicated definition, and it's not the one that we'll be using today. So there is a work due to Kato and Saito, which allow to express this number as follows. So you take the alternating sum, where the sum runs over 0 and 1 of, so here what I do. I take the torus of the diagonal in degree 2n plus I. So the square bracket means that I'm taking the G theory class of this guy, and then I take the degree. Of course, in this formula, there is a number n appearing from nowhere. And the point, and this is one of the main theorems due to Kato and Saito, is that if I take n large enough, the K-theory class of the store sheaf doesn't depend on n, and that only depends on the parity. So meaning that if I take n large enough, the store sheaf in degree 2n gives me the same class as the Tor sheaf in degree 2n plus 2. Okay, so long story short, this number is well defined and gives me exactly the number originally defined by Bloch. So next, I'd like to define this one conductor. So maybe let me fix here some notation. So I said that I'm assuming K algebraically closed. So the inertia group in this case is just the absolute Galois group of K, BK. And this group can be decomposed as follows. So there is a canonical exact sequence of groups, of topological profinite groups. So this is the inertia group. There is a unique pro-P-Silov subgroup, which is called the wild inertia. And the quotient is called the tame inertia. And somehow this number here depends on the action of this subgroup on the elliptic homology of the geometric generic fiber. So let me be precise. Now, I can look, okay, basically, by definition, the inertia group acts on the homology of the geometric generic fiber, so I can restrict this action to pi k. And this action is continuous. So now I have a pro-P group acting continuously on a QL vector space, meaning that these action factors through a finite group. So I can choose a finite Galois extension such that, so if I look at the wild inertia of the bigger field L, so this is a subgroup of pi k, this acts trivially on my homology group. We're almost there. So I fixed a finite Galois extension, and to such guy, there is a character I can associate to it. So let me denote by GLK the Galois group of this field extension. And there is a character called the Swan character, which is defined as follows. So to an element G, I associate, so the length of this module minus the order of the group plus 1 if G is equal to 1, or minus the length over OK of OL quotient by, so I let G act on a uniformizer of OL. So I fixed a uniformizer of OL. Sorry. I divide by pi L and I subtract 1. Okay, and there's one conductor. Can be defined as 1 over the order of the group And then I take the sum over the elements of the group. Actually, yeah. If you want. And then I take the trace, of course, any element in this quotient acts on this group by assumption. So I can take the trace of this endomorphism. And I put a weight, which is given by this character. Okay, so if the action, this character, if I take the sum all over G's, is 0. So the corresponding representation has no fixed points, meaning that if the action of pi k is itself trivial, this invariant is 0. Okay. So this invariant is really related to wild ramification. Where is that? Okay. So this is the formula. And in my talk, I'd like to discuss a proof of this formula, but as an intermediate, so as a maybe baby example, I'd like first to discuss a way to prove the formula I've just raised. So, recall, I'm giving myself a smooth and proper algebraic variety over a algebraically closed field K. And these assumptions ensure that if I consider the bounded, so dBco of this algebraic variety, and here I really mean the DG enhancement, not the triangulated category, for a reason I'll explain in a moment. So this is a dualizable object in the infinity category of K-linear DG categories. So this is the reason actually why I really need to work with infinity categories or their K-linear analog. It's because in order to talk about dualizability, I need a tensor product. And as far as I know, there is no tensor product on the category of triangulated categories. So here you really need to accept that there is no way out of the infinity categorical world. Anyway, what does this mean? It means that I dispose of an evaluation map like so. So here the tensor product is over dBco of K. And I can identify this tensor product with dBco of the product of Y with itself. And under this identification, this is just the pullback, so along the diagonal, followed by the push forward along the structure map. And then I have a dual map, which is the co-evaluation. So it goes in the other direction. Let me immediately use these identifications. So I need to go to dBco of the product. And this is given by Q upper star followed by the push forward. And these two maps satisfy the usual triangle equalities. So if I consider the composition evaluation tensor with the identity composed with the identity tensor with the co-evaluation. So this is a endofunctor of dbco of y, and this is homotopic to the identity and similar to the for the other way around. So this is what being dualizable mean. And then I can consider the categorical trace. So which is just the composition of the evaluation and of the co-evaluation functors. So this is an endo-digifunctor of dbco of k. And so it's an exact such functor. So it's uniquely determined by the image of the generator k. And so I can identify this with an object of this category, which is the composition. So I just need to apply this composition to the generator k. And this is just, yeah. What do I do? Such guy, which is by definition Hochschild homology of y. Okay? And then if I take the K-theory class of this object by the Hodge to the RAM spectral sequence, I recover one of the two terms in the Gauss-Bonnet formula. So this somehow tells me that this category retains the information of the algebraic invariant in the Gauss-Bonnet formula. And actually, one can also recover the other term. So in order to do so, one needs to dispose of a L-adic homology theory for DG categories. So this is work of Blanc, Robalo, and Vezzosi. And I'll just, okay, so for any DG category T, one can consider a certain QL vector space. I won't define this functor because the definition is quite complicated. It relies on the theory of non-commutative motives. But I'll just state a couple of important properties. So for example, it is compatible with the homology of schemes. So if I compute the L-adic homology of dbco of y, I get a two-periodized version of the homology of y. So yeah, this is an infinite dimensional algebra where I take these twists for all integer I. And another very important property is that this functor is Lax monoidal. So meaning that I have a map like this. but it's not an equivalence in general. But in the case of DB-Co, so if T equal W equal DB-Co, using the first formula here and the Cunet formula in L-adic homology, it is an equivalence. So this map is an equivalence. But here I'm really using the fact that somehow this category is of commutative origin. Huh? Really? Thanks. And yeah, so this formula implies that this guy is dualizable over this algebra. And from this, you can deduce that if you compute the trace, so the dimension, over this algebra of this guy, you get, so again using 1, you get the L-adic Euler characteristic of Y. And then the last step uses, there is a non-commutative L-adic Chern character. So this was introduced by Bertrand and Gabriele, relying on work of Marco and Taboada, which says that basically these two traces, this one and this one, as soon as I take the K-theory class, are compatible, so that I can deduce the Gauss-Bonnet formula. Okay, so there are 3 passages. I find a suitable category which is dualizable, and I somehow decategorify it in 2 different ways which are compatible. And the compatibility, so these 2 different categorifications provide me with 2 terms of the formula, with the 2 terms of the formula, and the compatibility of these 2 procedures tell me that, there is an equality between the 2. Okay. Now, how much time do I? There is an idea, going back to Bertrand and Gabriele, that the Bloch conductor formula, okay, maybe I forgot to say so. Okay, so maybe before I go on, as I didn't say, the Bloch formula was known in some cases. Sorry, I should have said so before. So known cases. So in characteristic 0, for isolated singularity, this goes back to Milnor, and it's known as the Milnor formula. For isolated singularity, so either if the relative dimension is 0, or if you have ordinary quadratic singularity, or if you work over a field, this is due to the ligne. So this particular case is known as the Ligne-Milnor formula. Then Bloch showed the case D equal 1. So the case of a degeneration of curves. And so actually, the precise connection between this formula introduced by Deligne and the Bloch formula was done by Orgogoso, who showed that the Bloch conductor formula implies the Deligne formula. Then Kato and Saito showed the case where the reduced spatial fiber is a normal crossing divisor. And yeah. And Takeshi Saito, maybe also Tomeyuka Abe work on this, prove the case over a field. Maybe also in between here, there is the case of characteristic 0 in general, which goes back to Sabba Saito. Who else? Kontsevich and Kapanov. In any case, many cases were known, but somehow a general proof was missing. And this is where Bertrand and Gabriele had an idea. That is, the non-commutative proof of this Gauss-Bonnet formula might be adapted to show the Bloch conductor formula. Okay, first of all, one has to identify who plays the role of DBCO in this setup. And here this role is played by this category. So this is by definition the quotient of dBco of the spatial fiber by dperf of the spatial fiber. So these two categories, there is an embedding of this guy into this one, which is an equivalence only when the scheme is regular. So somehow this category is an invariant of the singularities of my spatial fiber. And yeah, I guess it has been known for a long time that this category is related to vanishing cycles, which is a sheaf, an L-adic sheaf, whose cohomology, whose L-adic Euler characteristic computes the difference of the Euler characteristic of the two fibers. So somehow, I guess this is how they came up with this, with considering this category. Okay, maybe there is a theorem due to Orlov and Buchweiss saying that this is equivalent to the category of metric factorizations of X with respect to the uniformizer of the base DVR. So this is a category whose objects are ZMO2 graded vector bundles on X. So I have two vector bundles, and then I have two maps like so, such that the two possible compositions are a multiplication by pi k. And this immediately implies that this category it's not possible for it to be dualizable over K. So this is a K-linear category, because this tells me that this category is too periodic. Like the Ohm complexes are unbounded, which is something you don't want in dualizability. But what you can do, so the spatial fiber is by definition this pullback, and there is a canonical action of this derived groupoid. And here it's really important to take the pullbacks in the derived sense. Otherwise, I just recover small s, and I lose an important piece of information. Okay, so this action gives me an action of the singularity category of G. So this is a monoidal category because this is a groupoid. So I can convolute object in this category. So let me call this B. And this acts on T, which is the singularity category of the spatial fiber. And a theorem of Bertrand and Gabriele. Okay, so the precise statement is that if I take this relative tensor product, so here I should say something. This is a monoidal category, but it's not symmetric monoidal in general. So this is just an associative algebra in DG categories. Yeah, I can still take the relative tensor product. So here I have a left module. So the op here is taken in order to translate the left action to a right action so that this tensor product makes sense. In any case, what I get is that this tensor product is equivalent to the singularity category of this fiber product. And this implies that T over B is dualizable. So the notion of dualizability, since we are dealing with a non-commutative algebra, is a bit more involved. Mm-hmm.
Did you use a dualizability or this? Where did you use?
Well, to take this trace. I mean, the existence of these two maps satisfying the triangular is the dualizability. So in order to define this object in dB_co of K, you need to have a dualizable category. It's just like a vector space. I mean, you need the vector space to be finite dimensional, so dualizable, in order to take the dimension, right? It's the same thing. Yeah, the existence of the co-evaluation is the smoothness, and the existence of the evaluation is the properness. No, it's dualizable in B modules. I'll explain what I mean. Yes. Yeah, this is maybe in characteristic 0, this theorem was proved by Prayagraj, but here, I mean, the characteristic 0 situation was actually, the geometric situation was known. Here, the interest is mixed characteristic. So dualizability means that we still have an evaluation and a co-evaluation map. So the evaluation goes like this, and the co-evaluation looks and the co-evaluation looks like this. Okay, so I'm not taking the same tensor product here. Here I'm taking the tensor product over this bizarre algebra, while here I'm taking the usual tensor product over OK. And this map is B bilinear, so I can act with B both on the left and on the right-hand side here, and the map is compatible with this. While this is just an OK linear functor. Like when I take the tensor product, I lose the action of B. So first of all, I cannot, so I want to take the trace. but I cannot compose these two maps. So the solution is exactly to use the fact that this map is B bilinear. So I define the evaluation HH as so evaluation tensor with B tensor B over OK with B, where there is a reverse structure, I think here. So B rev is B, but whether I reverse the monoidal structure. So this is a functor from T op tensor B with T, which goes in B. So let me call this B nth. This guy. This goes to B tensor B over B nth, which is by definition the Hochschild homology of B over OK. Okay, so now I can really compose. So the trace of the identity of T over B is defined as this HH, evaluation HH, with the co-evaluation. And this gives me, so this is a functor from perfect complexes on S to this category, and it gives me an element. I can identify this with an element, with an object in this category. Now, there is a very down-to-earth problem here that this category is quite complicated. So I've constructed, so I didn't say, but this is a definition due to Bertrand and Gabriele. But somehow there is a problem that this category is very complicated and it's not clear at all. So I can take its K-theory class of this object, but it's not clear in which abelian group it lives. And this is work of myself with Dario. So we showed that there is a map. Oops. From the homotopy invariant K-theory. So we're systematically working with singular schemes, so I have to replace K-theory with homotopy invariant K-theory. This is not so important here. What is important is that I have a K-theory group here, which I don't know, but I can construct a map to Z, which we denote like circular integral for some reason. And so if I compute the integral of this trace, what I get, so the K-theory class, is the Bloch number. So somehow you should think of this as the analog of the first computation in the Gauss-Bonnet formula, right? When I extracted the difference of the alternating sum of the Hodge dimensions using some kind of categorical trace. This is the analog in the one parameter situation. Characteristic, in the geometric case, if you have a base field, there is so B is a commutative, is symmetric monoidal, in fact, so that you have a map like so, and Z is in fact the K-theory of B. The situation is much simpler. Here the point is really mixed characteristic. So we have to understand the topological side, the L-adic side. Yeah. So as I said, it is known that there is a connection between this category T and vanishing cycles. And I guess that the first instance of this connection is the theorem of Blanc-Robalato and Bezzosi. So I can take the cohomology of B, which acts on the cohomology of T. Okay, this is because my functor is lax monoidal, so it preserves actions. And they identify this with the action of, so as always, I have to work over QL beta. But here I'm taking homotopy fixed points with respect to the inertia. And this acts on the cohomology of this guy, which can be identified with, vanishing cohomology. I think I call this P. Yeah, I need to tensor with QL beta. And then take homotopy fixed points and take a shift. So maybe for simplicity, let me call this nu. Now, there is a, as I said, this functor is lax monoidal. So as in the case of the Gauss-Bonnet formula, I can consider the map induced by this lax structure. So this is the tensor product of the cohomology of T, and I land in the cohomology of the tensor product of the categories. And the point is that, in general, this is not an equivalence, which should be regarded as a positive fact, because otherwise, I mean, I will compute the Bloch number as the trace, as the dimension of this guy, which in general is not the right number. So this is exactly where the strategy, if you want, of the Gauss-Bonnet formula fails. Okay. Now, in order to understand what's going on, we'll need to rewrite the L-adic term of the formula. So it was written as the difference of the Euler characteristics minus this one conductor. Now, this can be written as the Euler characteristic of the vanishing cohomology. Actually, with a minus. And so this is not really compatible with what we are doing, because here I have fixed points, while here we have the whole representation. And here the key observation is that, no, I erased it. So before I introduced this one conductor, but this character, there's one character, but this character has a cousin, which is called the Artin character. So here I'm taking a sufficiently, yeah, okay, it's not necessary here, but I'm taking a sufficiently large Galois extension of the discrete valuation field, and I still have a function from the Galois grouped to Z, which is defined in a similar way, but not the same one. So if G is the identity, I need to take the length of Kähler differentials of this extension of dVRs, and otherwise I take the minus the length of OL modulo G pi L minus pi L. Okay. Now, the point is that G L over K acts on the vanishing cohomology as soon as I take homotopy EL fixed points. And this allows me to define the following guy. So me and Dario, we call this the Artin conductor of X over S. I think that in the literature, there is something called the Artin conductor, but it's not the same thing. And it's defined in the same way as the Swan conductor, basically. So here I take the sum over all elements of the Galois group. I replace this one conductor by the arting conductor. And then I take the trace over QL IL. So I have this algebra here, not QL. And I let act G on this vector space. And okay, actually, the arting character differs from this one character by augmentation representation. So using this, it's very easy to see that I can rewrite this guy as minus the trace over QLIK of the identity acting on fixed points of vanishing cohomology minus this arting conductor. And this is somehow nice because this is exactly what I can compute using this guy. But there is a missing step, namely, where does this guy come from? And I'm completely lost with my notes. Where am I? Yes. So now here I fixed a Galois extension. So I can take the spectrum of OL, so the ring of integers in L. And then I can consider, instead of the special fiber, the pullback of X along the canonical map from S prime to S. And this scheme carries a canonical action of this groupoid, which I denote by H. And just as for the special fiber, I get an action of C, which is the singularity category of H, which is a monoidal category for the same reasons. This is a groupoid, which acts on U, which is the singularity category of this guy. And actually, using results of Bertrand and Gabriele plus some results of myself with Dario, the cohomology of C acting on the cohomology of U identifies with, so I can take this algebra, and then I take the reduced group algebra on it via the group GL over K, which acts on, so I take the quotient of EL fixed points on vanishing cohomology over IK fixed points on vanishing cohomology. So this is somehow related to this, I mean, not the arting character, but these phrases. And there is a theorem which says that somehow at the level of categories, the information encoded by the action of B over T is the same as the information encoded by the action of C over U. Let me be precise here. So there is a result due to Dario and myself. It tells that the category of left B modules is equivalent to the category of left C modules. And this equivalence is provided by tensoring with this guy. So this guy is a left C module and a right B module. And I can take the relative tensor product on the right with B, and I gain an action of C. And this procedure, I can go back. And moreover, this module corresponds to this module. Now, this immediately implies that this module is dualizable over C. And what I get is such a diagram. Yeah. Okay, which commutes. And so now, if you remember, I have this map in L-adic homology, which is not an equivalence nevertheless, which is induced by this map. But now I have another map coming from the other direction. And what one can show is that if I take this guy, I get an equivalence. So somehow the cohomology of the piece in the middle decomposes as the sum of the cohomologies coming from these two pieces. And now, what I'm computing here is the integration. Okay, so the evaluation of the diagonal. So this coevaluation map corresponds to the choice of the diagonal. And now this decomposition theorem tells me that in the cohomology of this thing of the product, so which is the cohomology of this guy in the middle, I have the class of the diagonal. So the cycle corresponding to the diagonal. And in these other two pieces, so I get two other guys. And now, using this decomposition and this commutative diagram, one can show that, so the term coming from here computes the Bloch number. The term coming from here computes this term, and the guy coming from U. So this computes the trace over QL IK of the identity of nu IK. And this guy computes the Artin conductor. And then using the compatibility between the two procedures I've used, you conclude that the two terms in the Bloch conductor formula are equal. Yeah, sorry, I'm already late. Thank you.
Questions for the speaker?
So this is a very naive question because I'm not a number theorist. I mean, I don't have much background in number theory, but my understanding is that the original conjecture involves understanding wild ramification. I think you mentioned that too.
Sorry, the
original conjecture. I mean, the difficulty is understanding wild ramification.
Yes.
And so where in this, I mean, that conservation of difficulty principle means that somehow transported into some higher coherences or some derived structure. Where is, can you say something about the mechanism by which you deal with this wild ramification in this?
Where the wild ramification appears?
Yeah, and how is it dealt with? I mean, it's supposed to be technically very hard. So somehow by conservation of difficulties, it must be somewhere else, right? So where is it?
So if I understand correctly, your question, the point is here. So again, this is a character whose total sum, so if I take just this sum without the traces, I get 0. And if my extension is tame, all these numbers are 1. So this means that if I have no wild ramification, here I'm taking the sum of just the trace of the identity, because and the sum goes to 0. So this is where the wild ramification plays a role. Was this the question?
But it, yeah,
I mean,
somehow all this derived technology, let's say I don't know any derived algebraic geometry or higher category theory, and I'm just naively asking the question, somehow all this technology is letting you take some very hard thing in number theory and presumably solve it. So where, is it hidden in some higher coherences? Like where is the difficulty transported to? That's the question. And I had a second follow-up question on that, but that was sort of the...
I guess that the point is that, so, how to put it? So, where is the formula? Here I have this formula. Okay, so these are numbers and these are numbers. Yeah. Somehow you can categorify both. This is categorified by vanishing cohomology, and this is categorified by the localized intersection product of Kato and Saito. What higher categories do for you is to further categorify, and you put like a roof. So you have T over like this guy. You can categorify in one direction or in another direction, and then you can kind of close the circle. So just one categorification leaves you here. Like in order to conclude that the two numbers you get are equal, you need to get above here. This is what the higher coherences do for you.
Right. So do I understand correctly that somehow, I mean, there is a whole infinity two categorical story behind this?
Infinity two.
Infinity two, right? Because you're doing growth and decay Riemann-Roch. I mean, there's all that hidden behind making all this work, right? Is that true?
No, there is no infinity two.
There's no infinity
just
two?
Infinity one.
I think, isn't it, you don't need growth and decay duality? There's no growth and decay duality.
Of course, everything can be,
in the pipeline,
but you don't use the infinity two structure.
Yeah. Yeah.
Yes.
I see. Right.
Yeah, I didn't say. Yeah, I didn't say where the Artin character comes from, but yeah. Actually,
I'm surprised that it's so easy to, I mean, get rid of this problems of wild ramification. It's the thing I'm worried about is that, okay, so there's all this, I think you do need the foundations, the pipeline uses infinity two categorical machinery, right? No, not at all. No growth and decay Riemann-Roch. Only infinity one, okay. So, okay, but maybe we can talk later, yeah.
This construction of the integration here, this is hard, right?
This is quite hard.
There is a key.
I see. And that involves dealing with wild ramification? Or?
Why it's hard?
No, does that involve dealing with wild ramification?
I'm sorry, can you?
Wild ramification?
No. No. Yeah, I mean, depends. I mean, this block number sees wild ramification. It's just that you don't need to refer to a wild ramification to construct this. Like there are two separate problems. So as I said, there is two ways you can double decategorify. Either you first take the trace and then take a K-theory class, then, okay? Or you first take a vector space and then compute its dimension. I forgot what I wanted to say. Yeah, okay, so there are two separate things, like you have this B acting on T, you have to extract the Bloch number. That's one thing. And then there is another problem, which, I mean, if you don't care about the Bloch formula, it has nothing to do with the other one, which is extracting this term from the cohomology of this T. And then, I mean.
So maybe we can discuss later. Yeah.